Now we're going to wrap up our discussion of plane waves by looking at a final element, polarization. So this is something that applies to plane wave propagation that is not directly tied to transmission lines. And so I think it deserves a separate section for us to look more closely at. Now remember, one of the key differences is that instead of just a voltage and a current, so far we've been talking about an electric field in the x direction and a magnetic field in the y direction, and then having the wave propagate in the z direction. Right? So we have our electric field propagating in the x direction, we have our magnetic field propagating in the y direction, and then in the end, since after we take the cross product, we find that the power flow is in the z direction, right? But naturally, there's nothing sacred about x and y in terms of having it be perfectly aligned with the x or y axis, right? So how else can these sinusoids? So we can have a sinusoid, off axis, not in the x direction, but we can also have, what if we had one in the x direction and one in the y direction and added together? Right, so you can think from superposition. You can also have an electromagnetic signal that can be decomposed into two sinusoid waves, kind of one somewhat and both of them on the xy plane, and the magnetic field would also have similar qualities, and you add them together, and all that will result in a different behavior for the electric field and the magnetic field in terms of its propagation. And that is where polarization comes in. So let's just take a look at the simple description of, let's say the electric field is not directly in the x direction, right? So let's say the electric field, if we were to decompose it into the onto the x and y axis, the instantaneous form can be written as, we'll start with our regular electric field propagating in the positive z direction along the x. Now let's just say that it also has this other component that's in the y direction, that's along the y-axis, also e to the minus alpha z cosine omega t minus beta z, so also propagating in the positive z direction, but it has some kind of phase offset from the x direction, from the x-axis polarized electric field, right? So you have this propagating field in the x direction, you have a similar sinusoid in the y direction. The key thing is that they're not necessarily in phase, so there's this extra phi term here. So let's rewrite that into Phasor form. So in Phasor form, the subscript s just refers to a phasor, but I can also say it's a phasor by just saying it's a function of z and no longer a function of t. You can rewrite the Phasor form as some component in the x hat direction plus some component in the y hat direction, and separately there's a phase difference, right, e to the j phi, and then they both have e to the minus alpha z, e to the minus j beta z, so I'm just going to pull that out. So in the end, if you don't have just a straight up simple linearly polarized in the x direction wave, if it's propagating in the z direction, and you can break it down into something like this, right? There's an x component, there's a y component, and by projecting it onto the x-axis and projecting it onto the y-axis. And then we'll also, to make it super general, we'll also say they're not always in phase. Now, a few things I'll note here is that you can use Maxwell's equations to find H. So I'm just looking at the electric field because if I use Maxwell's equations, I can then use that to in turn find H, and then if I take the cross product of the two, I can find S. So for this turn, in this case, I'm just looking at the electric field in Phasor form. The second is that the phi describes whether the sinusoid in the y direction leads or lags the x component, right? And so depending on whether it leads or lags, that's going to change the component. And then also note that if you wanted to simplify it, to our clean, just in the x direction case, you just make EY equal to 0. And then separately, if you wanted to make this lossless, you just set alpha equal to 0. So this is kind of a more general form that can describe all situations. Now, in this case, we're going to look at 3 different polarization possibilities. One is linear, the other is circular, and the third is elliptical. So let's start with the linear polarization, which is probably the easiest to visualize. So the criteria for the linear polarization is that if phi is some multiple of pi, then that means that these two, the x and y components, are in phase. And so really all that means is that ex is that if you have your wave propagating, if I have this z coming out, so the wave is coming right at us, and you have x and y. In the first case, in our clean case, we originally just had our electric field kind of oscillating back and forth in the x direction as the wave comes out of the board right at you. But now in this case, if we have phi equal to some multiple of m pi, meaning this is, if it's a multiple of pi, if it's a 0, then that means that it's just ex and ey together. If there's remember, if it's pi, then this is just a -1. So basically, if these two are in phase, that just means that instead of going back and forth here, you're actually going back and forth at some angle, right, relative to the x-axis. So the wave is coming at you, and if you're standing here watching the wave come at you, the electric field is just oscillating in these two directions. And so that also means that the criteria, the Phasor form of this is that E is going to look something like Ex naught in the x hat direction plus Ey naught in the y hat direction, where this can be positive or negative, depending on whether m is equal to an even or an odd number. Next, let's